Let's talk average atomic mass. So we learned that for every isotope, it has its own mass number, protons plus neutrons, but we could have different isotopes of an element in a sample. And so that's where we get that average atomic mass, that decimal number on the periodic table, because we can't have fractions of protons and neutrons. So that decimal number must come from having different isotopes of the same element. So in this case here, we've got strontium as an example. And so strontium has 4 different isotopes here. So we've got strontium 84, strontium 86, strontium 87, and strontium 88. So all of those strontiums, if I look at my periodic table, I see it's number 38 on the periodic table. So all of these have 38 protons. It's just they have different numbers of neutrons. So 38 protons, different numbers of neutrons. And so to figure out the average atomic mass, we're going to use the percent abundance and the mass of each isotope. Now, you'll notice that here we're given that mass in a decimal number because technically we have this crazy thing called nuclear binding energy, where a little tiny bit of mass actually gets used to bind the nuclear particles together. And so that's why instead of it being 84, it's 83.9. Instead of it being 86, it's 85.9. For the sake of simplicity here, I'm just going to use the whole number. So if we are going to do this 100% correctly, we would use that decimal number because, again, that accounts for nuclear binding energy. So it's E equals mc squared. If you've ever heard that from our pal Einstein, energy equals mass times the speed of light squared. So a tiny bit of that mass actually gets changed to energy that's used to hold that nucleus together. So interesting, but to keep things simple, we're just going to use the whole numbers for our mass numbers here. Okay, so I've got strontium 84. That is in AMUs, atomic mass units. Another unit we use is grams for every mole. We haven't talked about the mole yet, but grams for every mole. So we've got 84 AMUs. We'll just use AMUs for now. And we need to do a weighted average. So we need to figure out how much of that 84 is actually part of the final atomic mass. And it tells us it's 0.56%. So I'm just going to multiply that by the percentage. And I'm going to do that for all of these. I'm going to multiply it by the percentage. So again, I've got 86 AMUs. That's 9.86%. Same thing with my 87 AMUs. And by the way, there's different ways you can do this. This is just one way I'm showing you. Mathematically, I'll show you another way that works the same. Times, and then we can see it's mostly 88. So if I was just looking at these numbers and I hadn't done my calculation yet, I would think, okay, well, my final answer is going to be really close to 88 AMUs because 82% of the sample is 88 AMUs. So my final answer is going to be really close to 88, but my other 3 isotopes are less than 88. So that tells me my final answer is going to be really close to 88 AMUs, but it's going to be a little bit smaller than that. So let's take a second and throw that in our calculator. Okay, so there's our numbers all thrown into our calculator. Our next step is we want to add all of these together. So let's make that into a little addition problem there. So I want to add all of those up. And when I add all of those up, I get 8,771.04. Okay, and so we are almost there. But obviously we said our number should be close to 88, and 8,000 is not close to 88. But that's because we just need to account for the fact that we're using percentages. So remember, percentages are parts of 100. So we actually need to divide those numbers by 100. Now here's where there's different ways to do the math. You could have done that from the beginning here. You could have written this as 0.0056. You could have written this as 0.0986, and this is 0.0700, and this is 0.8258, and multiplied that way here. And that would have taken care of the 100 right away. It's perfectly fine. Gets the job done right away. Or you can divide by 100 at the end. So the way we're doing it right now, we're dividing by 100 at the end. Again, we're just accounting for that percent. So this would be the math if we had 100. So we need to divide by 100, just again, to account for that percent. And when I do that, I get 87. My pen's being a little glitchy. So I get 87.71 AMUs. And if we think back, that tracks because we said our N number should be close to 88 because of this right here. The biggest percentage of our sample is that 88 isotope. But because all the other isotopes are slightly less than 88, that means our answer should be slightly less than 88. So close to 88, but a little bit smaller. And that's exactly what we have, 87.71. Close to 88, but a little bit smaller. So it's always good to go in at the end and do that little check and say, does this make sense? And in this case, it does make sense. So our average atomic mass of our sample is 87.71 AMUs. And that would be the number you would find on the periodic table for strontium.